In module 8 of chapter 9, we shall learn about a very important theorem for surface geometry, that is the Gauss-Bonnet theorem. At first, Bonnet in 1848 established this result, which was known to Gauss. This result is already known to Gauss in some different form, but Bonnet gave this form first. So, the theorem is named as Gauss-Bonnet theorem. Now, at first we shall learn about some preliminary concepts and propositions to prove this Gauss-Bonnet theorem, and in the next module we shall see some applications of this Gauss-Bonnet theorem. So, let us start to prove the Gauss-Bonnet theorem. The title of module 8 of chapter 9 is Gauss-Bonnet theorem with some applications. Now, here at first we shall learn about some preliminary concepts to prove Gauss-Bonnet theorem, and in this module we just only state the Gauss-Bonnet theorem. In next module we shall prove it. So, let us start the preliminary concepts to prove Gauss-Bonnet theorem. Just I have mentioned that Bonnet in 1848 AD published a theorem which was already known to Gauss, and it is one of the deepest and important theorem in the differential geometry of surfaces, which has enormous applications. Now, Gauss gave a relation between the interior angles of a geodesic triangle with the value of pi, and we know in our plane geometry that the sum of all interior angles of a triangle is 180 degree, that is pi, because in plane the geodesics are the straight line. So, in that case the sum of the geodesic angles are equal to pi, but for other type of surfaces, for spherical surfaces or for hyperbolic surfaces, the geodesic triangle, that means the triangle formed by geodesics, the interior angles and the sum of the interior angles is not exactly equal to pi. Sometimes it excess over pi or sometimes it less than pi. So, excess over pi of the sum of the interior angles alpha 1, alpha 2, alpha 3 of a geodesic triangle is equal to the integral of the Gaussian curvature. Gauss actually showed this result, that the excess over pi of the sum of the interior angles of a geodesic triangle is equal to the integral of the Gaussian curvature over the area of the triangle. That means, this is the relation what Gauss has proved or Gauss has invented, that is summation I equals to 1 to 3 alpha I minus pi equals to k dA for a region formed by the geodesic triangle. Now, suppose k equal to 0, then we have summation alpha I equal to pi, just I have mentioned it, that for Gaussian curvature is equal to 0, the sum of the all interior angles of a triangle is equal to pi. The triangle is formed by the geodesics of the surface, and for k equal to 0 the geodesics are the straight line. So, summation alpha I equals to pi. that is the sum of the angles of a triangle is pi. Now, when k equals to 1, then we have summation alpha I equals to pi plus area of the geodesic triangle. So, it is excess over pi when k equals to 1, that means the surface is a sphere or spherical, and here the sum of the interior angles of the triangle formed by geodesics are greater than pi. Thus, on a unit sphere, when Gaussian curvature is 1, the sum of the interior angles of any geodesic triangle is greater than pi, and the excess over pi is exactly the area of the geodesic triangle. So, that plus the additional part is actually the area of the geodesic triangle. Similarly, for k equal to minus 1, the sum of the interior angles of any geodesic triangle is smaller than pi. It is for hyperbolic type of surfaces where k equal to minus 1, the sum of the interior angles of any geodesic triangle is less than pi. So, Gauss-Bonnet theorem is an extension of the above facts to a region bounded by a non-geodesic simple curve. So, this portion actually the work of Bonnet given in 1848. Now, it gives us a relation between the topology of a compact surface and the integral curvature k dA, the double integration over the surface. So, this is known as integral curvature, and this gives the relation between the topology of a compact surface with the integral curvature. Now, before starting to prove Gauss-Bonnet theorem, we state the proposition without proof, because these proofs are beyond our scope to prove it here, but these are required for proving Gauss-Bonnet theorem. We just state the proposition. The first one is that if R u v is a surface with orthogonal curvilinear coordinate system or by parametrization of a neighborhood of a oriented surface S, and W s be a or omega s, whatever we can say, be a unit differentiable vector field along the curve gamma s, that is u equal to u s and v equal to v s, then the geodesic curvature of the curves on a surface is equal to 1 by 2 root within the first bracket a11 a22 and within the second bracket del a22 by del u dv ds minus del a11 del v du ds, the second bracket closed, plus d alpha I ds, where alpha is at the positive angle from Ru to Ws, where Ws is the gamma dash s in Si Si plus 1. So, within this interval, these are the angle formed between Ru and gamma dash s. Now, the next proposition, the statement of the next proposition is this one: if gamma is a mapping from 0 to 1 to gamma s, that means it is a curve, is a simple closed piecewise regular parametrized curve with vertices beta si that means for each arcs the vertices are beta, beta Si, and the external angles are theta I, where I is from 0 1 to m. Then summation I equals to 0 to m alpha I Si plus 1 minus alpha I Si plus I equal to 0 to m theta I equal to plus minus 2 pi. So, this is the theorem for turning tangents. The proof is beyond our scope. So, we just state the proposition, and this plus minus sign depends on the orientation of the curve, gamma. So, these are the two important propositions which will be required for proving the Gauss-Bonnet theorem. Now, see the figure about the last proposition, that here S1, S2, S3 are the arc lengths actually, and they are forming the angles theta 1, theta 2, theta 3 like this, and the vertices are beta 1, beta 2, and the gamma is the whole curve. So, from this figure we can understand the previous proposition. Now, we shall also prove in this module this result, that if the curvilinear coordinate system is orthogonal, we know that the curvilinear coordinate system will be orthogonal if A12 equals to 0. We have learnt earlier. Then the expression for Gaussian curvature of a surface is given by this k equals to minus 1 by 2 root A11 A22 within the third bracket del U1, and in the first bracket 1 by root A11 A22 del A22 by del U1, the first bracket closed, plus del U2 again in the first bracket 1 by root A11 A22 del A11 del U2, and the whole thing is closed by the third bracket, where A is the actually the determinant of A alpha beta, which is not equal to 0, and actually we can replace this A11 A22 by this A, because A12 is 0. Therefore, we can replace this root over A11 A22 by A, and A11 A22, the product should not be equal to 0, otherwise it will not occur. So, this is the value of the Gaussian curvature for a surface with orthogonal curvilinear coordinate system. Now, we shall prove this one. This is very important result which will be required to prove Gauss-Bonnet theorem. Now, using the definition of Christoffel symbols, it can be shown on surface that R alpha beta gamma delta equals to 1 by 2 within the first bracket, this expression del 2 A alpha delta by del U alpha del U gamma plus del 2 A beta gamma by del U delta del U alpha, and all these things with the in the second components we have the Christoffel symbols of the first kind with the product of A theta eta. So, this is the expression of R alpha beta gamma delta, and we can easily find this expression from the definition of R alpha beta gamma delta, where we know that alpha beta gamma delta is running from 1 and 2, because we are on surface and they are the surface indices. So, R 1 2 1 2 will have this expression is equal to half del 2 A 1 2 del U 2 del U 1 plus del 2 A 2 1 del U 2 del U 1 minus del 2 A 1 1 del U 2 del U 2 minus del 2 A 2 2 by del U 1 del U 1 plus A theta eta, and within the first bracket all the Christoffel symbols of first kind, that is 2 1 comma eta, 1 2 comma theta minus 2 2 comma eta and 1 1 comma theta. Now, when the coordinate system is orthogonal, we have A alpha beta equal to 0, because alpha beta is running from 1 2, that means A 1 2 equals to A 2 1 are 0, and the reciprocal tensor of A alpha beta, that is A upper alpha beta, equals to 1 by A alpha beta. So, putting these values in the above equation, we have this expression R 1 2 1 2 equals to half minus del 2 A 1 1 by del U 2 minus del 2 A 2 2 by del U 1, and this one is within the first bracket, plus A theta theta, and within the first bracket all these Christoffel symbols of first kind. So, the second term, due to the product of A theta theta, we have the Christoffel symbol of second kind. The first part is the same. So, R 1 2 1 2 will have this expression, where the first part is same as previous one, but the second part we have the Christoffel symbols of second kind, that is A alpha theta within the first bracket gamma alpha 1 2 gamma theta 2 1 minus gamma alpha 1 1 gamma theta 2 2. And if we break all these values of theta and other surface index from 1 and 2, we have this expression R 1 2 and 2 equals to the same, the first part is remaining same and the second part is coming to this one A 1 1 within the first bracket all the products of Christoffel symbols of second kind plus A 2 2 again all the Christoffel symbols of second kind. So, R 1 2 1 2 takes the form in this way, half within the bracket the previous expression, and in the second portion we are putting the values of the Christoffel symbol of second kind, that is gamma 1 2 gamma 1 2 1, all these expressions we are putting or substituting, and you are getting A 1 1 within the bracket del log root A 1 1 by del U 2 the whole square plus 1 by 2 A 1 1 del A 2 2 del U 1 del log root A 1 1 by del U 1 plus A 2 2, and the similar fashion we are getting the expression. And simplifying the above expression, we are getting this R 1 2 1 2 equals to, again the first portion is the same, we are getting the same one. The second portion we are simplifying and it is coming to A 1 1 within the first bracket 1 by 4 A 1 1 square, and again del A 1 1 by del U 2 whole square plus 1 by 4 A11 square del A22 del U1 del A11 del U1, the bracket closed, and again similarly for A22 has the same type of factor. Again simplifying this, we are getting a very big expression for R1212, this expression. I am not telling all these terms individually. So, we can understand after simplifying this, we are getting R1212, and again simplifying, we are getting a very rigorous expression, that is R1212 equals to minus half root A11 A22. Within the third bracket, it is coming del del U1, and within the first bracket 1 by root A11 A22 del A22 by del U1 plus del del U2 within the first bracket 1 by root A11 A22 del A11 del U2, and the bracket closed. Now, we know that the Gaussian curvature, the definition of Gaussian curvature, K is R1212 by A, obviously A not equal to 0, and for orthogonal curvilinear coordinate system, it becomes R1212 by A11 A22, because A12 is 0. So, the value of K is this one. So, therefore, the expression for K is coming to this minus 1 by 2 root A11 A22, and within the third bracket del del U1, within the first bracket 1 by root A11 A22 del A22 del U1 plus del del U2 within the first bracket 1 by root A11 A22 del A11 del U2. We can also replace in place of A11 A22 by A, where A is determinant of A alpha beta. So, with the help of these two propositions and the result obtained, we are in a position to state the Gauss-Bonnet theorem, and which follows like this, that if S is an oriented surface with an orthogonal parametrization, that means the curvilinear coordinate system is considered orthogonal, and if R is a simple region of S, and let gamma be a curve such that del R is the boundary of R, that means the gamma gives the boundary of the region R, where gamma is positively oriented, parameterized by arc length S, and if beta S0 dot 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 beta Sm and theta 0 theta 1 dot 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 theta m are the vertices and external angle formed by gamma, then the expression for Gauss-Bonnet theorem is this one, the summation I equal to 0 to m integration Si Si plus 1 kappa gs ds plus the double integration r k dA plus theta I equals to 0 to m is equal to plus minus 2 pi, where kappa gs is the geodesic curvature of the regular arcs of gamma, and k is the Gaussian curvature of S. So, this is the statement for Gauss-Bonnet theorem given by Bonnet in 1848, and the proof will be given in the next module, because the proof is a lengthy proof and it is rigorous proof. So, we shall prove this theorem in our next module. In module 8 of chapter 9, we have just stated a very important theorem for surface geometry, that is Gauss-Bonnet theorem given by Bonnet in 1848. This theorem was actually an extension of Gauss' result, and here in this module we have just stated two propositions which will be required to prove this Gauss-Bonnet theorem, and the proof will be given in the next module. And here we have also proved a result that if the curvilinear coordinate system is orthogonal, then what will be the expression for the Gaussian curvature of a surface. So, with this we end this module, and in the next module we shall see the proof of the Gauss-Bonnet theorem.